Hello everybody. In this video, we're going to talk about gradient and directional derivatives, which is partly from section 14.5. And the key concepts we want to introduce is gradient and directional derivatives. And this section is based on partial derivatives we've covered at the beginning of the course and the vector analysis or linear algebra in the previous video. So what is directional derivative? Or what are we looking for by directional derivative? So we can imagine there is a mountain, a territory, and you're supposed to look for fast way to go to the peak of the mountain. But suppose you are given a vector u, two-dimensional vector u, which is, here it is written as u1i plus u2j, which means it is the same thing as u1 and u2. So this, in the plane, this gives you how you move, the direction you are moving. So suppose you're instructed to move along this direction, u1i, u2j. So every u1 horizontal step, you want to move u2 vertical step. That's the direction you're going to. So suppose this is the direction you're moving, then your height, your position height, will be changed along the mountain surface and maybe decreasing, maybe increasing. So this is the change. How fast does it change? So the rate of change of f is considered to be your position height on the surface of the mountain area. So this height. So the rate of change of your position height in the direction of u at the current point p0 is the rate at which f changes along this line at p0. And this is called directional derivative. So basically, by directional derivative, we mean rate of change. In mountain surface, this is rate of change of your height when you move. And directional means, because this is two dimension, so there is a moving direction you are going to move. It could, so this is instructed, or this is given direction. So directional derivative is the rate of change along the given direction. That's what it means. Now, how should we define that? By formal language or mathematical formula. So the derivative of f at p0, x0, y0. p0 stands for your current position. By x0, x coordinate, y0, y coordinate. So the derivative or rate of change of your height at current position x0, y0 in the direction of the unit vector u equals u1, u2 is defined as a number. So this is the left-hand side is the notation of directional derivative. So df ds u p0 is given by limit s goes 0, and this is ratio in your height, f of after move minus your position of your height at current position before move. So this is rate of change by along this u direction, and divide by s, your step size. So provided the limit exists. So this is formal definition, and the directional derivative, the notation is usually adopted by textbook in either way. So du f p0. D is differential, u is the direction you're moving, and f is the function or mounting surface, and p0 is your position, current position. Or you can write duf, and p0 is written as a subscript after the bar. So it's called the derivative of f in the direction of u evaluated at p0. All right, this is formal language, and we will see how to solve or how to compute this rate of change or direction derivative using gradient. So now we need to introduce the gradient. What is gradient? We can first recall the partial derivative of function of two variables, f of xy. So when you talk about partial derivatives, there are two kinds of partial derivatives. One is partial derivative with respect to x, which can be written as fx. Another one is called fy, which is partial derivative with respect to y. Then you get two numbers. If you put them together, if you have two numbers and you can put them together in a column, then this is a two-dimensional vector. And this is called gradient of f. Or you can write in this way using I and j special vectors. I stands for 1, 0, and if we use I as 1, 0, we reserve this notation, this symbol, and j is 0, 1, then this is equivalent to what it says here. So gradient f is the vector consists of two partial derivatives. And if you are given a point, current position, then you can evaluate this gradient f by plugging in its x0 and y0, its xy coordinate, which is evaluation of the gradient, or the value of the gradient vector, obtained by evaluating partial derivatives at the point p0, x0. You can write this in different ways, but this is all natural. All right, there are different ways people often call this notation, gradient f or grad f or del f. It doesn't matter, as long as you understand what it means. All right, then here is the theorem, practical theorem, which should be used in the actual computation. So our original motivation is when you move in a certain direction u, how fast do you change? How fast your height is changing. So this is direction derivative. And the definition was given by this, and we're not, in practice, we don't use this often. This is only used to prove, but for the computation, we're going to use this formula. So this is the directional derivative, or you can write this as du, derivative along u of f given p0. That's the same notation. And then the theorem says it is dot product of gradient f and u, the given direction. So we can highlight this formula. This is the real formula we're going to memorize. So let's look at this computation, this example, and we're trying to understand the theorem 9. So there is a mounting surface given by fxy in a formula, and your current position is 2, 0. Now you're going to move along the direction of this. This is not direction vector because direction is required to be unit length, but this is obviously, the length is v length is 3 squared plus negative 4 squared, which is 5. So this is not direction, but it says if you move in the direction of this, then what is the direction derivative? The derivative. So first of all, we can see that the vector you are moving to, so the moving direction is not directly given. We have to find it out. So that if we say that direction you're moving along is u, then this is normalized vector. So v over by its length, divided by its length. So normalized by its length, which means v over 5. V is 3i minus 4j. So you can write this as 3 over 5 and negative 4 over 5. This is one kind of notation. If you prefer, you can write this way. Either way is fine, but now we got the direction. So the problem itself gives the direction you're moving to implicitly, not directly, not explicitly, but you need to find it out, the direction you're moving to. Now it's clear where you move. And then for directional derivative, we know that duf is gonna be gradient f dot product u. So u is here, so we don't have to worry about this anymore, and gradient f is not here. So what is gradient f? We know that gradient f is just nothing but put partial derivatives together in a vector, and when I look at fx, then we freeze y values. So this is e to the y, first term. Second one is cosine xy. We have to use chain rule. So cosine derivative is negative sine xy. And then by chain rule, you are looking at xy partial derivative with respect to x, which is y. And for fy, we freeze x. In other words, e to the y derivative is itself, so x e to the y. And cosine derivative is sine xy. And by chain rule, you need to take another derivative for xy, but this time variable is y, x is frozen or coefficient, so it's basically x. All right. Now I am interested in the point at 2, 0. So now it's ready to put 2, 0. So replace all x by 2 and replace all y by 0. Then e to the 0's power is 1, and minus whatever, this is sine 0 is 0, so this is entirely 0, so it is 1. The second line is when I put this 2 times e to the 0, which is 2, minus the whole thing, because sine 0, 2 times 0 is 0, so the whole thing is 0. So the first term, it gives you 2 only. Now we are ready to answer the question. What is duf given to 0? And then it is gradient f, which is 1, 2, dot product, the direction 3/5 and 4/5, but don't forget negative sign, that this matters. And then the dot product gives me 3/5 and minus 8/5, which is negative 1. So what does it mean? By negative 1, the ratio of change, the rate of change is negative 1. Negative number means you're going down the hill, not going up to the hill. Positive sign means increase your height. Negative number means in terms of rate, negative sign means you're decreasing your height. Now we're going to discuss further about direction derivatives and the relation between gradient, which gives meaningful interpretation of these computations. So we have the formula, direction derivative, which is gradient dot direction. And by dot product, we can recall if you have two vectors, u dot v, dot product of two vectors, then that means u magnitude, v magnitude, and cosine theta. Theta is the angle formed by vector u and v. So if we apply this formula, then it becomes magnitude of gradient f, magnitude of u, but remember, the magnitude of u is 1 because u is direction. So anything multiplied by 1 is itself. So, and then cosine theta. Here's theta is the angle between your actual moving direction and the gradient f. Gradient f is another vector, which means it's pointing to a certain direction, right? So when I continue this formula, then when I realize u has length 1, then we come up with this formula. So duf can be written as gradient f cosine theta. All right, what does it mean? So we are going to analyze 3 special cases. Now suppose you're going you want to go as fast as possible to the peak of the mountain. Then you're looking for the direction, move yourself as fast as you can. Then this is the rate of change. You want to increase this as much as you can. Then in what direction do you want to go? If you want to maximize, we know that mountain itself, there's nothing you can control. But theta forms the angle between, so suppose this is you're moving along, and this is gradient f. So u is something this is your step direction, moving direction. You can control in whichever you want. So, and theta is this angle, the angle between these two variables, two vectors. So to get this as big as possible, I want cosine theta as big as possible, which means I need cosine theta equals 1 because cosine function has maximum at 1. At what angle that gives you 1? The answer is theta equals 0. In other words, your moving direction and gradient f should agree. You want to go along gradient f. So this means gradient f as a vector, it's pointing to the fastest route to the peak. So if we write this in, what I said is basically formula summarized in this line. So duf equals gradient f and cosine 0, because you take theta equals 0, which is just gradient f because cosine 0 equals 1. So f increases most rapidly in the direction of gradient f. Now, if you want to go home, you want to go down the hill as fast as you can, then what do you want to do? So the answer for going up is you must go along gradient f. This gives you fastest way to going up. If you go home going down, then we want to go opposite direction. Intuitively, this is true, and theoretically, we can prove that because f won't decrease. If you want to decrease your height as fast as you want, then you take negative gradient f, because when you look at cosine theta, you want to take cosine theta as small as possible, and the minimum of cosine theta is negative 1 when theta gives pi angle or 180 angles. So duf is gradient f cosine pi, which is negative gradient f. So the conclusion is f decreases most rapidly in the direction of negative gradient f. Now another question. Now you are hiking and you don't want to climb up the hill or down the hill. You just want to go along a trail which is flat in the middle of the hill. Then which direction you should go? If you go, we already know that if you go this direction, increase the height. This direction, then decrease the height. But in which direction you are maintaining your height, then which means the ratio of change has to be 0. You don't change. So I want this guy as 0. Then cosine value becomes 0 when it is pi over 2 or 90 degree, theta 9 over degree. So if theta is 90 degrees, so in other words, gradient f is pointing here, which is pointing to peak, then what you want to do is you are going 90 degree to this gradient f, which directs you a trail which in the flat way. So 90 degree perpendicular. And this way is 0, the ratio of change. So here, that any direction u orthogonal to a gradient f is a direction of 0 change. All right, now we are going to look at next example quickly, which applies the properties we've analyzed. So example 3. So here is a mountain with a surface given by 1/2 x squared plus y squared. We know that this is paraboloid. It's not really a mountain, it's a valley, I think. Right, now the concern is our question is in which direction you should go to increase most rapidly at the point 1, 1 and decrease most rapidly at 1, 1, and what are the directions of 0 change at 1, 1. Well, so we can quickly write its formula. You need to go gradient f direction at 1, 1, which directs you to the rapid increase, and negative gradient f 1, 1 gives you down the hill track, which decreases you, and then you want to find some u which has perpendicular to the gradient f. Then this u is your answer. So perpendicular vectors have dot product 0. So we need to use that to find this u. All right, with this in mind, we're going to, so I don't need to copy that. So we can have another page, and if I remember correctly, this is fxy equals 1/2 x squared plus y squared. And the first question increase rapidly. So I want to translate to the math language at this. Then that means gradient f is fx, fy, and you put 1, 1 here. All right, then what is fx? For this easy problem, frozen variable is y and activated variable is x, so this is x. Fy is y, so and 1, 1, then this is 1, 1. But you want direction. If you stop here, you are going to lose points. So it's not unit vector. We know that you need to normalize that. So we know that gradient f, this is square root of 1 square 1 square, which is square root of 2. Then normalize that. You want to find u is gonna be 1 over square root of 2, 1, 1. If you want, you can write this as square root of 2i, 1 over square root of 2j. This is all good answer. And the second one is opposite. You don't have to repeat any calculation, just to decrease rapidly. So we can look at negative u, which is negative this number, just opposite the previous answer. Now the third one, we know we want to find u which is orthogonal to this direction or perpendicular to this direction, or this is the same direction as this. So we can, for simple calculation, I want u which is perpendicular to 1, 1. What does it mean? I want u with 1, 1 dot product equals 0. What kind of u you can get? Then maybe I will write v in this way. So, yeah, u. And then what kind of u can be, can do this job? We saw that negative 1, 1, 1, 1, give it 0, because this is negative 1, this is 1. So is that, then can we suggest u equals negative 1, 1? It's not, because this is not unit length. We have to divide by 1 over square root of 2. So this way, we have go horizontal. And this way, we go decrease most rapidly. This way, we can get increase. All right, there are a few obvious formulas, algebra rules for gradients. So gradient of sum equals sum of gradients, and all those things are given, and there's a quotient rule, product rule. You can review it by yourself, and whenever we use it, we come back and revisit these rules. All right, we're going to stop